Well, good morning, afternoon, or evening. I'm Professor Rios, and welcome to week 6. This week, we address two topics, so human fingerprint on climate change and precipitation and clouds. So this is an updated set of slides and a video based on updates using AR6 information. So if you happen to have an older version of this, please delete it and make sure you download the latest version on Brightspace. So whatever is on Brightspace, whenever you do check in during week 6, should be the most recent version of the presentation, including the video. So having said all that, let's get going. We'll begin with this presentation here. So human fingerprints, literally the things that tell you that only because of human intervention these things happen, right? So human fingerprint on climate change, the hypothesis being global warming is a result of industrial emissions of greenhouse gases. Remember, we are artificially making the greenhouse effect more efficient. That's a key thing to know, by adding more greenhouse gases into the atmosphere, thereby trapping infrared radiation when it is re-radiated in the form of long-wave energy from the surface and then bound back from clouds and other gases like CO2 and CH4 and water vapor. All right, so that's the basic hypothesis right there. In other words, human activities. Again, remember, the greenhouse effect would exist regardless of whether we were around or not. We're just simply making the greenhouse effect more efficient. We're making that blanket thicker, so to speak. So number one, there is more industrial carbon in the atmosphere, meaning carbon that has been released as a function of industrial activities. So carbon comes in 3 flavors, if you want to think of them: isotopes. An isotope is a molecule with different number of neutrons. So basically, carbon-12 is lighter than 13, which is lighter than 14. Make sense? Carbon-14 is the heaviest. Plants and algae basically prefer carbon-12. And carbon is fixed during the photosynthetic process. The process when a plant takes CO2, solar energy, water, and converts it into a carbohydrate or sugar, and expelling oxygen into the atmosphere. So coal and oil have a low 13 to 12 ratio, meaning there is more C12 than there is C13, because plants, algae prefer carbon-12, and coal and oil come from plants. When you burn this coal, you basically release more of the lighter carbon-12 into the atmosphere, and therefore more CO2. So think of it as a 12C for 12 carbon, and then O2, oxygen, creates a lighter form of carbon dioxide. So that can be measured, okay? So you can measure the ratio of carbon-13 to 12 in the air as fossil fuels are burned, meaning you put more of this into the air. The ratio of this to this decreases because this number becomes bigger, that's smaller, that becomes smaller. You can measure this in ice cores, in corals, and other sponges. And basically, in the last 200 years, the Industrial Revolution, there is more carbon-12 in the atmosphere. So that's just a very basic bottom line issue. So humans are responsible for this really dramatic increase in CO2. And here it is. So roughly from about 1750, this is generally believed to be the beginning of the Industrial Revolution. So it began to go up. And then in 1958, we began to measure it rather well. And that increase has been pretty dramatic since then. Less heat is escaping into space. Remember, we're making the blanket thicker, right? We mentioned that earlier. Therefore, you're trapping more of the heat into the bottom layer of the atmosphere, which is referred to as the troposphere. The oceans are warming from the top down. So the layer is 75 meters or by 500 meters, and it's a hotter ocean. So this hotter ocean is more easily able to exchange heat between the top of the ocean and the atmosphere. And that has a significant implication when it comes to the energetic nature of storms such as hurricanes. But it doesn't just have to be a hurricane. It could be a nor'easter or just a simple regular winter storm or thunderstorms out in the ocean. Okay, so consistent with the increase in greenhouse gases is basically the acidification of the oceans as well. The more CO2, the more acid the water is, because you combine CO2 with water and you create something called carbonic acid, which is what regular rain actually is. Regular rain is generally slightly acidic, but we're making it more acidic. Number 4, nights warming faster than days. So the sun heats the air during the day, air cools at night, you know this. Now, days would be warming faster than nights if only the sun activity increased, right? But greenhouse gases are keeping that heat in at night, so the nights are actually warming faster than days are. More heat is returning to the Earth. Remember, we're putting more CO2 and CH4 into the atmosphere, therefore we're making that re-radiative capability of the atmosphere more efficient. So with gases such as these 3, in addition to others, we have enhanced that greenhouse effect. This is really probably one of the most significant points in this entire course. From the beginning to end, this is what you need to get. This is like the big key takeaway. We have enhanced the greenhouse effect. Therefore, we are making the ability of the atmosphere to re-radiate infrared energy back towards the surface more efficient. Satellite measurements show this. If it was the sun, there you go, winter is warming faster than summer. If it was the sun, winter and summer would warm essentially about the same rate, the same amount. The seasonal contrast really wouldn't change. Under an enhanced greenhouse effect, the winter warms faster. Summer is already warm, right? It's already a warm season, although you can get more extremes in there as well. But the seasonal contrast begins to decrease. The stratosphere is cooling. We've addressed this already in a previous lesson because we have amplified the greenhouse effect in the troposphere or near the surface. We prevent some of that escaping heat to make it to the stratosphere, which is the next layer above. And as a result, satellites show that the stratosphere is cooling while the troposphere is warming. Number 8, physical models require human greenhouse gas emissions. So these are called general circulation models. And we're not going to get into the specifics of a GCM. They are super complicated. They're very, very mathematical, and they're very, very complex. But these are the big mathematical simulations of the atmosphere. And they require human greenhouse gas emissions in order to mimic what we see. Okay? So they predict global climate for the 20th century. You can sort of go back in time. You can run them from the past into the present and then into the future to see how good they are. If you input only natural factors into these models, meaning the sun and volcanoes, and please pay attention to this part, GCMs would actually be predicting that we would be cooling at the moment. Again, this is if you take humans out of the equation. and you only account for the sun and volcanoes, GCMs predict global cooling. If you add in greenhouse gases to the input, GCMs predict that global warming would match what we've actually have seen since the 20th century. And here's a really, really good example. This is from the AR6. So these are observations, meaning this is reality. This is what's been observed. So the temperatures sort of go up and down, up and down, up and down. And then in the last, 170 years plus, boom, this spike in temperatures. Now, this bar here, this sort of green color, would mean what would happen to temperature if you only accounted for the sun and for volcanoes. So this right here. And notice how it would basically remain pretty close to what we considered zero or normal and slightly cooler. But this is when you consider natural and anthropogenic, there's that word again, human-aided forcings. And by now, the idea of forcings and anthropogenic should mean something to you. If they don't, you need to go back and review. Anthropogenic is human-aided, and a forcing is something that makes the atmosphere system either warm or cool. Okay? Number 9, multiple independent lines of evidence. That means that there are many, many, many things that all sort of point to the same conclusion. Humans are having an effect and an impact. Prior to Industrial Revolution, we probably didn't have that much of an input, or an impact rather, but we do now. So this is a summary of all of them. Other fingerprints, statistically significant human effect. So you can also point to a decline in sea ice, rising sea level, extremes, so temperature and rainfall events, for example, and a change in a general atmospheric circulation. So again, this is pretty straightforward. Again, all temperatures have increased with the exception of Antarctica. So the bottom line is how well the global circulation models predict temperature changes. Again, using only the sun and volcanoes. They do not match observations. Using natural and human factors, including greenhouse gases, models match what we actually see. Okay? So here's another way of looking at it, the observed warming driven by emissions from human activities. So you can actually sort of break it down: carbon dioxide, methane, nitrous oxide, and so on. The red contribute to positive forcings, right? And the blue contribute to negative forcings or cooling. Blue cooling, red warming. Make sense? And here's the example. We have warmed up. You've already answered this question in a quiz. 1.09 degrees Celsius. There it is. And how much of that has been as a result of total human interference, well-mixed greenhouse gases, other human activities? When you add it all up, you get to this sort of gray bar here on the far left of the image. So that's that first lesson. It's really, frankly, rather straightforward, but it's important that you understand the lingo, the terminology, things like the idea of forcings and anthropogenic and anomalies. See how it all sort of goes back to the first 4 lessons of the term? You need to really sort of review that if some of those terms have basically fallen out of your memory bank. You need to, because they will keep coming back. So that's the first lesson. Now we're going to move on to something slightly more specific, and this would be precipitation and clouds. So let's put that into presentation mode. Now, clouds are some of the least understood meteorological parameters simply because we have only had satellite observations dating back to the 1960s, whereas we've had weather observations at weather stations going back to the 1700s, not in every location. Clouds have only really been observed by satellite, which is an amazing tool going back to the late 1960s. That's it. So there isn't as big a body of data out there that you can go back and study and examine. So let's look at overarching AR6 conclusions. So here's what, and this is a lot of wording, so I'll leave it up for a few seconds and you can stop it and read it. This is me sort of condensing what they said. Climate change is bringing multiple different changes in different regions, which all increase with further warming. Here's a couple of examples. Climate change is intensifying the water cycle. This brings more intense rainfall and associated flooding or drought. Because remember, the amount of water vapor in the world is fixed, but perhaps the distribution changes. Climate change is affecting rainfall patterns, regardless of latitude. So here's an example. In a warmer climate, evaporation and rainfall increase. In a warmer climate, air can contain more moisture within it, meaning the N2s and the O2s, meaning the nitrogen and the oxygen that make up what you breathe, are more spread apart because the air is warmer, so it expands, so it can contain basically more water vapor inside of it. So as a result, while the relative humidity may remain constant, you can put more water into the atmosphere, and that can translate into rainfall, bottom line. So, greater evaporation, more water. Average relative humidity is constant, but the percent of saturation doesn't really change. So, bottom line, more water into the air. So, as the partial warms up, the water holding capacity of that partial increases, and as a result, you can basically have more water vapor content, which eventually translates into precipitation. So here's a really good from Climate Central. As your temperature increases, every 1 degree Fahrenheit, there is a 4% more water vapor capacity in the atmosphere. And the atmosphere has warmed up by about 1.96 Fahrenheit or 1.09 Celsius since the year 1850. So that's roughly that about 7%, actually almost 8% in water availability in the atmosphere. This image right here is, I know it's a little bit difficult to grasp. This is from the Summary of Policymakers, AR6, Precipitation Projections for Individual Regions. So this is the world you're looking at here. I know it's weird, right? So you see the different, here is what SCA means, Southern Central America, SCA, get it? ENA, Eastern North America, Central North America, Western North America. So they have broken the world into these little regions, and basically anything in the green means an increase in precipitation. Anything with dash lines means low agreement. Anything in the yellow means a decrease. So generally speaking, there is either limited data or areas where the scientists think there's going to be an increase in heavy precipitation events. Okay? Again, this is they're taking the world and they're breaking it up into individual little, how many? Hectagon? No. Pentagon is 5, septagon 7, whatever 6 is, I think is hexagon. I could be wrong. In any event, these little geometric figures, northeastern North America, northwestern North America, basically Canada, Greenland and Iceland, get it? Europe, Africa, and so on. So that's how they sort of break the planet down. This is also from the Summary for Policymakers. showing you that projections for either a planet that warms up to 1.5, remember we're at 1.09, 2 degrees, or 4. Notice some places actually get wetter. And you might say, well, that's good. Well, it is, but maybe it isn't. What if all the rain falls at once? Is that good? From an agricultural point of view, not really. Here is the idea of heavy precipitation likelihood. In other words, likelihood of heavy precip over land that once took place every 10 years in the context of current and projected warming scenarios. So for example, presently, what once used to take every 10 years, now it is 1.3 times more likely to occur. In a 1.5 degree scenario, it'll be 1.5 times as likely to occur. In a 2 degree warming scenario, it will be 1.7 times as likely to occur. And in a 4 degrees Celsius hotter Earth, it is likely to occur 2.7 times as often. So right now, we're basically about 6.7% wetter than we were between 1850 and 1900. That increases to 10.5, 14.0, and 30.2. That's just to give you a sense of how likely are you going to be to see these increased precipitation events. This is the idea of soil moisture. So now this isn't precipitation. This is how much moisture is retained within the soil. And this is a big deal because if you're into agriculture, right, growing food and all that, that makes a big, big difference. So this is for a 1.5 degrees Celsius scenario, a 2 degree scenario, and a 4 degree scenario. And these are not temperatures, but 0.5 standard deviations wetter, 1 standard deviation wetter, 1.5 deviations wetter. So from the norm. Heavy rainfall events are increasing. Again, we already addressed the idea of warmer air, higher moisture capacity. Here's an example from northwestern European flooding in July of 2021. So this would be in places like Germany, the Netherlands, Belgium, and France. Okay. So it gives you a sense of it has an impact on fatalities and injuries and, of course, infrastructure. Again, just to give you a sense of the real world impacts these events can have when rainfall falls too quickly. Here's an example of Hurricane Harvey over Houston, Texas, and southeastern Texas in the year 2017. Again, this is something you hear a lot in the news, and I frankly struggle with it because now everything gets blamed on climate change. And while some things you can begin to sort of logically arrive at that conclusion, is everything a climate change issue? There were strong hurricanes in the 1990s, 1980s, 1970s, 1960s, get it? There were heavy rainfall events, tornadoes, hailstorms, all kinds of severe weather prior to climate change being considered an event or a thing to think about. So you sort of have to be careful. This is tricky because you hear this a lot in the news. Okay? But the whole point, I guess, this package of slides is trying to get at is flood events are more likely in a warming world because remember, for every degree Fahrenheit that the atmosphere, for every 1 degree Fahrenheit increase in temperature, the atmosphere can contain about 4% more moisture, which can then translate into precipitation. about drought. So drought is measured by what's called the Palmer Drought Severity Index. It uses temperature and precipitation data to calculate water supply and demand. And it really functions as a long-term drought measurement, okay? And here's a basic conclusion over the past 100 years. It's not a very palatable conclusion. There's not much. It just simply says that droughts have increased. There's a possibility that perhaps we're more aware of droughts. There's a larger data set out there that one can point to. So this is still being sort of fleshed out, quite frankly. But drought has a significant impact, of course, on agriculture. And here's the example from AR6 using the same mapping scheme of using these little shapes for areas of the world. Notice how there's a lot more of these, low agreement. So this is less well understood compared to just basic precipitation. The areas that have a decrease, an increase in drought or a decrease in drought, it's only one of those. But notice how there are far more that have either low agreement and the type of change, meaning increase or decrease. It's not really well understood. And notice how the confidence, basically confidence is either low or medium. You don't really see one single one where the confidence is high. So that's poorly understood is what I'm trying to get at. And again, using the same setup as before, but using agricultural and ecological droughts and drying. So from 1850 to 1900, every 10 years it would happen once. In the present scenario where we are, 1.7 times as likely, 2, 2.4, 4.1. So it makes sense that while in a warmer world we might have more severe rainfall events, we might also have more significant drought events happening at the same time, but in different areas. So one area gets too much rain while another area gets not enough or any. So that's the idea here. In clouds, so what about clouds? Again, they're poorly understood because they haven't been studied as long. Low clouds shield the surface and reflect sunlight. They induce a negative feedback. They cool the earth. High clouds have the opposite effect. They trap heat. So they have a positive feedback. Remember, negative is counteracting. Positive is reinforcing. That's the key takeaway there. Climate models disagree on the effects of clouds. The satellite record, as I mentioned, is too short for really any true meaningful trends that match the same kind of trends we understand for things like precipitation and temperature. So the IPCC report in 2021, there's a better understanding of cloud feedback mechanisms at all altitude levels. That's good. And in summary, there's a stronger understanding of feedback processes in individual cloud regimes since AR5, which took place in about 2013. So the overall assessment here is that positive net cloud feedback can be at least be thought of as there's a high confidence that that's actually taking place. Again, clouds are still less well understood compared to precipitation, heck, even compared to drought, because we have been measuring temperature and moisture a lot longer than clouds. So the records don't match, but that data set is getting better. And that is the presentation for both of these slide sets. I hope this one here, climate fingerprint, pretty straightforward. This one is as well. there's just perhaps less confidence in what some aspects of this, especially clouds. Again, that's a function of there's just not that much data out there yet. But that body of work continues to improve. Anyway, hope you have a fantastic week. If you have any questions, please let me know. Ask. Come to the Zoom office hour or ask for one that works for your schedule. Send me an email. We can talk on the phone. I mean, there's a whole different variety of ways to connect. So in any event, hope you're doing well. And we'll talk to you soon. Bye.